All right. So we are finishing out our final exam review, looking at whatever questions from the final exam review you guys would like to look at. Uh, it's a nice set of 20 of them there. There's only 17 on the final exam itself. Um, so it's a pretty good, pretty close match. Unlike Cal 1 has 50 questions in their practice final review. So, as bad as 20 is, hey, it's not 50. So, which question would you guys like to look at first?
Um, Operations with logarithms. I got these web.
So that's let's see, 16 and 17. So there's 16. Let me just yoink a picture of 17 as well. Posted a message saying, "Thank you. Now to teach my last class of the semester." And everybody is like hearting that. So that's why my phone keeps making noise. I'm like, but I'm actually teaching. Shut up. All right, so when we're looking at log properties, it can go one of two ways. So I can start with a single logarithm that I'm going to split apart into a bunch of separate logs, or I can start with a bunch of separate logarithms that I'm going to zip back up into a single logarithm. So you have to be comfortable using the log properties in both directions when you get to calculus. On the final exam, though, I'm only going to ask this question one of the two ways. So this is a pair of questions that only corresponds to a single question on the final. And this one is a free response, but there's not actually a whole lot of work here. Like I have some people who can just like look at the problem and write the answer. I would like one line of work in between, please. All right, so when we're looking at our log properties here, I'm going to take the second one because the numbers on it are uglier. So the natural log of a to the negative third over b to the negative ninth, c to the eighth. So when we're looking at a single logarithm that we're going to be expanding, we want to focus on what the order of the operations are. So I have a to a power, b to a power, and c to a power. The b and c are being multiplied, but the bigger operation, the more outer operation, is the big fraction, the division there. So the first operation we're going to focus on is splitting this by the division. There. So when we have the log of a fraction, that becomes the log of the top of the fraction minus the log of the bottom of the fraction. Now, since it was natural log, I'm writing natural log for the logs, but whatever log base you have, just keep the same log base everywhere. So this log property is log of a over b equals log a minus log b. I'm not going to give you the log property on the test, but this is the property that's being used. Log of a divided by b becomes log a minus log b. Or when we get to the second problem, we're going to work it backwards. When I have log a minus log b, I can zip it back together as a fraction. Now our next property involves multiplication. So when I have the log of a product, that is going to become the log of one part of the product plus the log of the other part of the product. So since it's b to the negative ninth times c to the eighth, I write natural log of b to the negative ninth plus natural log of c to the eighth. Now, what I am doing here, though, is I am saying that this whole expression here is being replaced for the single natural log I had above. So when I'm making that substitution, I need to put parentheses around it. And I especially need the parentheses here because of that minus sign that's in front. That minus sign is actually going to get distributed through to both parts of this product, or this sum now. So I can write it as the natural log of a to the negative third minus the natural log of b to the negative ninth minus the natural log of c to the eighth. Yeah, to the log. So it's in front of, it's being distributed as a negative one. So it's just negative one times natural log of b to the negative ninth. So I can just write that as minus. But if you want to write the ones in front, like that's fine. So our initial step was using that log of a product becomes the sum of two logarithms. Now, our last log property is the power rule. Log's whole purpose in life is to take powers and bring them down on the line. So the log of a raised to a power is the same as the power times the log of a. So all of these have powers, so I'm going to bring those powers down, and they're going to multiply in front. So negative 3 times the invisible 1 here is just negative 3 natural log of a. Then I have a minus 1, and I'm bringing down a negative 9. So that's going to become like minus 1 times negative 9 with the natural log of b, but I could just write that as plus 9. And then again, the negative 1 times the 8, that's just going to become minus 8 with the natural log of c. Now, if you're really comfortable with your log properties, like I very often will go from the first expression to the expression where it's like natural log of the top thing minus natural log of a bottom thing minus natural log of the other bottom thing. So anything on top of the fraction is positive, anything on the bottom of the fraction is negative. And then I bring down all the powers and multiply them, and then I end up at that end result. So that is our end result. Typing it in on the results up here is a little weird. So we'd put negative 3 in front of the natural log a. Then we'd put a plus and a 9. And then we'd have to put a minus sign from the drop-down box and an 8 on the natural log c. If you put plus negative 8, webwork will get confused. But that is how we take a logarithm and break it all apart, unzip it. So does that make more sense? Now, if we get the flip way, the zipping it back up way, I'm going to take this guy here, log of x minus 3/2. Oops, sorry, put the parenthesis in the wrong spot. Log of y plus 7 log of z. So I'm going to use my same log properties, but I'm going to have to use them like backwards order. So I'm actually going to have to use the power rule first. So this 3/2 and the 7 are going to have to come up as powers. The log x doesn't have a number in front, so it's just going to hang out as a log x for this step. You could technically move this as a negative 3/2, or you can leave the minus sign. It doesn't matter which. The answer will be the same. It'll just be typed a little bit different.
Excuse me, so the exponent has to be positive.
It doesn't have to be. I could write it as y to the negative 3/2. I'd just then have a plus in front here instead of a minus. So both ways will work. I just usually leave the minus sign because that's usually the way webwork wants like the final answer to work. But mathematically, they're totally equivalent. All right, now that I've moved my powers back inside the logs, now I can focus on my operations. So I've got a minus sign here, and then I've got a plus sign over here. So I'm going to do these one step at a time, and I usually just go left to right. You can, though, technically rearrange the order as long as the minus sign stays attached to the log y to the 3/2. So if you wanted to put the log z to the 7th plus log z to the 7th first and put those together first and then deal with the y, that totally works as well. I just usually take it in the order given. So these guys are going to merge together and become the log of x divided by y to the 3/2. So I went from 2 logs to a single log. I went from subtraction, and that changed into a division sign. The positive one divided by the one that was being minused. Yep, because the negative sign is getting represented by the fraction. If you had it as the negative 3/2 power, then it would have been a plus and it would have been a product. So you'd have x times y to the negative 3/2. But I could rearrange my fraction here. I could move the y from the bottom to the top by changing the sign of the exponent. So that's just like where you're moving it in the problem versus like where the minus sign went. Like it all ends up being equivalent. All right, now our plus rule says we multiply those results. So now to be the log of x over y to the 3/2, and then times, like next to the fraction, z to the 7th. And we can type it like this. Usually, though, we merge it into one fraction. So the log of x z to the 7th over y to the 3/2. Normally, the directions say write your result using only positive exponents. So if you had the y to the negative 3/2 on top, like the final result usually is like move it to the bottom. It'll take it either way, though. You could write it x, y to the negative 3/2, z to the 7th. It took that. Like any of those results are good. Just remember when you're typing the answer on webwork, webwork already wrote the log in front for you, so you're only typing what's inside the logarithm.
Is there like any specific order of operations for the log properties that we should follow, or is it okay to just use them for?
So the only like caveat is I did the power rule first because when we look at our log properties for the difference, the quotient and product, there were no numbers in front of the logarithms. So I use the power rule first, but then you can use the sum and the difference one in whichever order you want. Just as long as anything that has a minus sign ends up on the bottom or ends up with a negative power. So that's the nice thing about the log properties. As long as you get the coefficients put up first, the rest of it is very interchangeable. So really, it's just a matter of practicing them to get comfortable using those properties over and over again. Now, the number of times you may want to practice it, that depends more on you and how many times it takes you to learn something. And I don't know if these questions have a show me another. Worst case scenario, you can load up the math textbook. This is section 6.3, scroll to the bottom, and there should be a bunch of example problems you can work. There may or may not be like answers in the back of the book somewhere.
Is there any other resources that you can recommend? Like we need to like solve practice problems other than textbook?
So if webwork won't generate extra practice problems, then I usually go to the textbook. And then if you need answers, it's kind of a pain, but I would basically just type the question in Google, and AI is now pretty good at generating the answer. It's also pretty good at generating an explanation of the answer too. Like it's kind of a double-edged sword. Every once in a while it's wrong, but for pre-cal questions, it's usually on track. Sometimes you can even just take a screenshot and post the screenshot. All right, what's another question you guys would like to look at?
Question 20 would be a good one.
So we are going to have 19 and 20 are both log equations. 20 is just a little bit weirder. So you're going to have one log equation to solve on the test, and it's worth 10 points. So the only difference between 19 and 20 is 20 starts with the logarithms on different sides of the equation. So our first step is going to be to make this one look like the previous one. So in order to get my logarithms together, I need them all on the same side of the equation. So I'm going to add log base 4 of x minus 11 to the other side of the equation. Now, it's real tempting when you've got them listed with the plus here to try to add the insides. Don't do that. Logs have their own special properties. So right now, we were just moving the term to the other side of the equation. So just write it on that other side of the equation. Now we can use a log property. So what does my log property tell me when I have log of a thing plus log of another thing? Yep, I can write it as a single logarithm, log base 4, of the product, x minus 5 times x minus 11. I'm just putting some brackets to say like all of that is inside the logarithm. Yep. If they were different log bases, we would be like up the creek. Like we we don't solve equations where the bases are different because none of our log properties work then, and we're just like, I don't know what to do with this. Like you end up arguing with one of the logs to force it to be in terms of the other log, and it just gets you end up using the change of base formula and it gets messy because you end up with this extra division constant that, yeah. But it in a real world context, you don't end up with logs with different bases in a problem like. All right, so now that it's a single logarithm expression equal to a number, now I can cancel out that single logarithm. So how do I undo log base 4? Yep, the 4 base exponential. So the 4 caret on both sides of the equation. Or you can use the exponential like rewrite base 4 to the second power equals the inside of the logarithm. Now 4 raised to the second power, 4 times 4 is 16. So there is me using my handy dandy log properties and then my log exponential inverse property. And now I have a quadratic equation. And it's factored, but it's not equal to 0. So it's real tempting here to be like, oh, x minus 5 equals 16 or x minus 11 equals 16. No, that only works. We can only do that split property when it's equal to a 0. 16, there's an infinite number of ways I can multiply stuff to get 16. So it could be 1 and 16, or 16 and 1, or 2 and 8, or 4 and 4, or 32 and a half. Like, too many ways to multiply to 16. So instead, we're going to have to FOIL this thing out. So x squared minus 11x minus 5x plus 55 is equal to 16. And then we're going to minus the 16 in. So now there is that 0 we need. So I have x squared. I got a couple of like terms in the center. Negative 16x. So x squared minus 16x. And then 55 minus 16 is plus 39. So now that my quadratic is equal to 0, now I can solve this using my normal quadratic solving skills. So we can use the quadratic formula here, and that will give you the 2 results that x equals. And if that's your preferred way of doing it, absolutely, totally works every time. We are deliberately, though, producing a quadratic that factors. So x squared I can only get from x times x. 39, not a lot of ways to multiply 2 numbers and get 39. 1 and 39 are too far apart to give us a 16, but 39 is divisible by 3, and 3 goes in there 13 times. So 3 plus 13 is 16, but I want negative 16, so I'm going to make both of them minus. So x minus 3 times x minus 13, that is our factored form. And now that it's a product equal to 0, the only way 2 things being multiplied equals 0 is if one of the 2 things is 0. So either x minus 3 equals 0 or x minus 13 equals 0. I don't know which one is true or false, so I just set them both equal to 0 and solve. So I'm going to have x equals 3 or x equals 13. Sorry. So with the log equation, logarithms have restricted domains. So not every x value is going to work in the original equation. So one of the ways to figure out which answer is good or bad is to figure out the domain restriction based on the original equation and then figure out what the numbers do in relation to that domain restriction. Usually, though, I just do it by checking the answers back in the original equation. So I'm going to plug x equals 3 in here. So everywhere there's an x, I'm going to put 3. And now I'm going to do the little bit of algebra or arithmetic. So this becomes log base 4 of -2. Nope, I can't take the log of a negative number. That right there is enough to say, nope, x equals 3 is thrown out. Over here, we also get a negative, log base 4 of -8. So like double 8, cannot use x equals 3. But when we come down here to check x equals 13, the 13 actually works. I get log base 4 of 8 equals 2 minus log base 4 of 2. So this equation only has one solution, x equals 13. X equals 3 is excluded because it's not part of our permissible domain. When I try to plug it in, I get bad math that I can't evaluate. So all of our math here was correct. We did all of the algebra. We used our pre-cal skills. All of this was correct. It's just when we start using the log properties and condense the logarithms into a single expression, the single logarithm has a broader domain than the separate logarithms. So x equals 3 is actually a valid solution to the equation we had before we did the 4 exponential. It works in the single log equation, but it doesn't work in the 2 log equation. So when we're checking answers, we always have to go back to the very original equation. So on the exam, you're going to have to do the whole log property. You'll get a quadratic that you've got to FOIL out and move the number over, and then factor that new quadratic, and then check the answers. Now, if you're running out of time, typically the smaller answer fails and the bigger answer is the one that works. So if you're like, oh my God, I'm running out of time, just box the bigger answer and I'll pretend you checked it. So this one can feel like a fair amount of a time investment. It's not a short problem. So that's part of why it's worth 10 points. But some of the other questions on the final are much shorter. You're not going to have to do as much work, especially if you remember how the problem works. So some of the questions are longer, but some of the questions are much shorter. And on any of the multiple choice questions, if you like guess and happen to pick the correct answer, you get full points. If you show your work and pick the correct answer, you get full points. If you show me work and pick the wrong answer, I will still give you some partial credit. So if you're confident on a multiple choice question, you don't have to show me work. But if you're not 100% sure of your answer, I'd recommend showing some work just in case. Now, some of them just don't have a lot of work to necessarily be shown, but all right, what's another one y'all want to look at? Yeah, number 6 asks us to find the inverse. And it's been a hot minute since we did one of those. And by a hot minute, I mean 2 months. So finding the inverse, the general procedure for finding an inverse of a function is to swap x and y and then get y by itself, solve for y. Well, our original expression is in function notation, so our very first thing is actually to write the y in there. So this is y equals x over x plus 1. Now, everywhere there's a y, I'm going to write an x. Everywhere there's an x, I'm going to write a y. So there's my swap x and y step. So now I have my weird equation, x equals y over y plus 1, and I want to solve for y. Trying to solve anything with an algebra fraction is like, please no. So our first step is get rid of the fraction denominator. So I'm going to multiply by my denominator, y plus 1 on both sides. Now, because I'm doing careful math, I use parentheses everywhere. Very safe. My y plus 1 in the bottom cancels out the y plus 1 I chose to multiply by. So on the right side, I have y by itself. But on the left side, I also still have a y. So even though it feels like I got y by itself, when we say solve for y, we mean there's only one y and it's by itself. So if there's more than one y, we got to do more work. So this y plus 1 thing times x, I'm going to need to distribute that x through. So I have xy plus x equals y. So to get our y's together, like, so we only have a single y, I need them on the same side of the equation. Now I could move the y term to the left and move the x term to the right. That will totally work. I'm a little lazier though. I'm just going to move the xy to the right side. So now I have x by itself equals y minus xy. Now that these are on the same side, they both have a y. That y is in common, so it is a common factor. So I can write y times, and then I write my results from pulling the y out. So I had y by itself, so I need a 1 as a placeholder, minus, I pulled the y out, so that leaves an x. So my factoring result is y times 1 minus x. If I remultiplied that, y times 1 is y, minus y times x is xy. So this is equivalent. Now, our goal was to solve for y. I now have just a single instance of y. So I want to keep this y here and get rid of what I'm multiplying by. So I undo multiplication with division. So I divide by 1 minus x. So I have y equals x over 1 minus x. Now, if you solved it a different way, if you minused the y and minused the x, your result would be negative x over x plus 1. Either of those are correct here. And then the very last step is just to trade out the y for the f inverse of x notation. But on webwork, you're just typing in whichever formula you got. So this one is actually a multiple choice question. So technically, on a multiple choice question, you can work from the answers back, um, or you could even technically compose the answers with the original function and see which one undoes everything. I don't recommend either of those because they are more work and more complicated work than just finding the inverse. Now notice our original function was x over x plus 1. Our inverse is not x plus 1 over x. The inverse is not the reciprocal. The inverse is doing all the operations inside out and backwards. So we have to swap the order and swap like the operations themselves. When you have an algebra fraction, the inverse gets really hairy. So there's not an obvious like, oh yeah, if I just like swap this thing here and do this thing here, like poof, there's my answer. Algebra fractions, there's not a good consistent way to reason through it, especially a fraction that has the x showing up in more than one spot. Now, some other functions you can kind of like unpack it a step at a time and get through to the inverse function, but when the function has x in more than one position, that's where the inverse gets really hairy. But the algebra skills we're using on this problem, you're going to have to use combined with log properties in calculus. So that's why, even though this question feels like really obscure, like when am I ever actually going to need to know the inverse of a random function? You won't. But the algebra skills we used, solving for y when y shows up in more than one spot, that you are going to use.
Is there like going to be formulas like on the exam or?
So all of the formulas that are on exam 3 are going to be on the final. And it's going to be, so on the front of the test, it'll look like the front of the exam 3, but the very last page of the exam is also a rip-off sheet that has a bigger unit circle and all the formulas. So that way you can have it next to your exam, so you're not having to do the page flip to try to write down formulas. Because I know some people made typos from trying to do the page flipping. If you want to bring highlighters to like highlight formulas when you're using them, or to have like a post-it that you can put on the formula sheet to just be like, this is the formula, like feel free to do that. That is actually a really good hack for if you're dyslexic. It's kind of a pain if you're reading a full book, but for something like pulling a math formula, putting a post-it right underneath the formula, like technically doing one above and below, like really does it. So you can see this is the formula I am reading. All right, what's another one y'all want to look at? 7? So 7 and 8 use, I think it might actually be like 7, 8, and not, no, 7 and 8. Yeah. So this is asking us to work with the sum and difference formulas. So one of the steps in solving this problem is to look up the formula for cosine of a plus b from the front of the test. So the formula here is cosine alpha cosine beta minus sine alpha sine beta. So in order to solve this, I know right now, I know the sine of alpha is 9 over 19. So right here, I can fill in 9 over 19 in place of the whole sine alpha. And then I also know cosine beta, which I have here, is negative 7/19. So I can write negative 7/19 in place of cosine beta. But I still need to know what sine of beta is, and I need to know what cosine of alpha is. So to figure out those other two missing pieces, I'm going to have to construct the triangle for alpha and beta. So for alpha, they tell me alpha is between 0 and pi over 2. So that's quadrant 1. So if they tell us where the angle is, we better draw it. And then there's our alpha labeled, that angle that's on the vertex, on the origin. And then they tell us sine of alpha was 9 over 19. Now remember our hippies. So some old hippie caught another hippie tripping on acid. So SOH, OH. So where is our hypotenuse in the triangle? Yep, the diagonal side. So this side over here, that was not the color I wanted, is 19. Our opposite side is the vertical side across from the alpha. So there's our 9. So I just need to figure out my horizontal side. That is a right triangle, so Pythagorean theorem. So we have x squared plus 9 squared equals 19 squared. Now on the test, the numbers are not going to be this ugly. Heck, on the test, the problem is actually more straightforward than this. Yeah. And then we minus the 81. So that gives us an annoying 280. And then we square root both sides. And we have to answer our plus or minus question. Because we're in quadrant 1, we're going to keep the positive square root. Now, in the past, webwork has made us actually reduce that square root, but on this one, it'll actually work with it. So now that I know x is the positive square root of 280, now I can actually say I know what cosine alpha is. Cosine alpha is going to be that adjacent side, square root of 280, divided by the hypotenuse of 19. All right, now same song, second verse. We know the cosine of beta is negative 7/19, and they're telling us beta is between pi and 3 pi over 2. So pi is our negative y-axis. 3 pi over 2 is our negative x-axis. So this is quadrant 3. So cosine is adjacent over our hypotenuse. So that puts our negative 7 on the x-axis and our 19 on the hypotenuse. I need to figure out my third side, so another Pythagorean theorem. So negative 7 quantity squared plus y squared equals 19 squared. So 49 plus y squared equals 361 minus the 49. So 362 minus 50, so 312. And then we square root. So we have to answer the plus or minus question. When we look at our picture, what is our y going to be, positive or negative? Yep, negative because we're going down. So that means my sine of beta opposite that negative square root of 312 over my hypotenuse of 19. So in place of sine beta, I'm going to write negative square root of 312 over 19. Done. So on the test, you are absolutely going to have questions where you've got to draw the triangle, find the third side of the triangle, so you can then figure out what one of the trig functions is, one of the other trig functions. Like you're going to have a question that does that. There's also going to be a question that uses the sum and difference formulas. So problem 7 here is actually like a hybrid of different parts that'll show up in different places on the final. But these are all things that we've been doing over and over again. We've done the whole triangle setup, find the third side of the triangle over and over and over again. Our double angle formulas, like if it asked for sine of 2 alpha, we could answer that. I know what sine alpha and cosine alpha is. I can look up the formula and use those pieces in the formula. Or if it was cosine 2 alpha, I could look up the formula for cosine 2 alpha and use the pieces. You don't have to find the max and the min. So that was problem 5. So let me throw it up there. So all you need to do on the test is everything except the max and the min. So this one is a free response because trying to write this as a multiple choice would be a giant headache because then it'd be like different amplitude numbers and different, no. So free response, but like on some of them for the amplitude, it's like, what's the amplitude? 5. What's your work? Writing the number 5 in the blank next to amplitude. Like there's not really work for doing the amplitude. But that's our a value in front of our function. So a value for amplitude. Our period comes from the b value. We got to remember the formula for the period. B looks like we're multiplying, but b is an inside quantity and the inside lies. So we're going to take our normal period for the sine graph, 2 pi, and we're going to divide by b. So even though it looks like b would stretch, multiply by 2, we'd really divide by 2. Or in this case, our b value is really wacky. It is pi over 4. So 2 pi divided by pi over 4 is the same as 2 pi times 4 over pi, multiplied by the reciprocal, and the pi's cancel, and we just get a period of 8. All right, now I'm going to skip down to the bottom, phase shift. That's coming from our x minus or x plus thing inside the function. So x minus 3, with the factored form, 3 is our phase shift, but which way is it going to go? Yep. It looks like negative, which would normally be left on the x-axis, but the inside lies. So we're going to go 3 units right. So not a lot of work on the phase shift, like you're basically just writing the answer. That's okay. Now our midline, this is going to ask for the midline equation. So it's not just a number here. It needs to be an equation. Now the midline is the horizontal middle of the graph. So the halfway point between the high and the low. On a normal sine graph, that horizontal line is y equals 0. This particular graph, though, has a +3 at the end. So it's saying, do everything this graph says and then add 3 to all your results. So it's taking even our midline and adding 3. So we're just taking whatever that d value is, 3, and it's y equals that d value. So if it was -2, it would be y equals -2. So the drop-down box will have the x equal or the y equal, and then you just put the number. On the test, though, you're going to have to remember to write the whole equation. Now, for finishing the problem out for web work, the max and the min are take the midline value and add the amplitude, or take the midline value and subtract the amplitude. So we'll have 3 + 5 and 3 - 5. So we get 8 and -2. So not all of the free responses are long. Some of them are just free response because the multiple choice would be a headache. This problem used to be much worse. It used to be, here's a graph. Which of the equations is this graph? Like, it's a really good think about it question, but it takes some time and it frustrated people, I think, more than it was worth. Mhm.
Are you able to go over problem 11?
Mhm. All right, so problem 11 has given us an equation to solve. So we have 2 sine of 3 theta equals the square root of 3. So our goal here is to figure out what theta values make this equation true. And because this is 3 theta, there are actually 6 solutions. A normal sine of theta equation produces 2, but when we have 3 theta in there, it's going to multiply the number of solutions by 3. So there are 6 solutions. Now it won't be 6 on the test because 6 is ridiculously long, but it will be more than 2. So 2 sine of 3 theta equals square root of 3. I'm trying to get theta by itself. So the first thing I've got to contend with is that outermost part, which is the 2. So I'm going to divide both sides of the equation by 2. So I have the sine of 3 theta equals the square root of 3 over 2. Now this is where we go to the unit circle. So there are 2 places where the sine value is square root of 3 over 2. Sine is our y value. So there's one of them in quadrant 1. And then there's our other in quadrant 2. That is literally where the sine is square root of 3 over 2. The angle values that correspond, we got to go with the radians. So I have pi over 3, and I have 2 pi over 3. Those are my numbers from the unit circle. But it was sine of not theta, but sine of 3 theta. So these are 3 theta equals pi over 3, and 3 theta equals 2 pi over 3. But we're also forgetting whenever I pull a number from the unit circle, I also need to account for all the coterminal angles. So that's where the 2 pi k shows up in our formula. So when I pull from the unit circle, I put the plus 2 pi k. Especially when what this unit circle is equal to is not just a variable. If there's an extra number in there, I absolutely need the 2 pi k. So now, to get theta by itself, I need to get rid of that 3. So I'm going to divide by 3. On the other side, though, because there's a whole lot going on, I'm going to write it as multiplying by 1/3. So now theta is by itself, but that 1/3 needs to distribute through. So pi over 3 times 1 over 3 becomes pi over 9, plus 2 pi k times 1/3 becomes 2 pi k over 3. And then similarly, our other equation becomes theta equals 2 pi over 9 plus 2 pi k over 3. So that is our general solution. But that is not the list of solutions from 0 to 2 pi. So to generate that list of solutions, I need to use k values. Now the k values I always start with are k equals 0. And I only need to use as many k values as there were being multiplied to theta. So since it was 3 theta, I'm going to use 3 k values. K equals 0, and then k equals 1, and k equals 2. So with k equals 0, theta equals pi over 9 plus 2 pi times 0 over 3. Well, that's just pi over 9. So there is our first solution. Likewise, our other formula is going to produce 2 pi over 9 plus 0. All right, now when we plug in k equals 1, though, we've got pi over 9 plus 2 pi times 1 over 3. So pi over 9 plus 2 pi over 3, well, I need a common denominator, so I'd multiply by 3 over 3. So I've got pi over 9 plus 6 pi over 9. That gives me 7 pi over 9. And then one more time, 2 pi over 9 plus the same 2 pi over 3, 6 pi over 9. So I get 8 pi over 9. So there's my next two solutions for my list. And on the test, you'd be done. There's only 4 of them. But webwork had to be a little extra, so we got to do it one more time with k equals 2. So pi over 9 plus 2 pi times 2 over 3 still needs a time 3 over 3. So 12 pi over 9 plus a pi over 9 is 13 pi over 9. And then 2 pi over 9 plus 2 pi times 2 over 3 times the 3 over 3 12 pi over 9 plus 2 more pi over 9 is 14 pi over 9. So all 6 of those are the solution to this equation. So you will have one question on the final where you're going to have to mess with the k values. It's a free response, so you can still get partial credit, close credit, all of that.
Are you able to go over problem one, just as a refresher?
Mhm. So problem 1 is asking us about a domain. It's giving us 3 functions. You're only going to have to do one function on the test. There is actually a second domain question about a logarithm. But for this one, it's going to be the ugly one, which is, in my version, the last one. So domain restrictions come from dividing by 0, square rooting negative numbers, or logging negative numbers or 0. So when I have a square root number, my domain restriction is whatever is under the square root must be greater than or equal to 0. Whatever is on the bottom of the fraction, that is not allowed to equal 0. So I can solve this non-equation by minusing the 2. So this tells me x is not allowed to be negative 2. And then if I finish solving my inequality, I minus the 8. I have that x is greater than or equal to negative 8. Now I need both of these statements to be true. So I'm going to jot down my number line. Negative 8 to the left, negative 2 to the right. So x is not allowed to be negative 2. Negative 2 gets an open circle, and everything else would be true. Our x is greater than or equal to negative 8. So at negative 8, I'm allowed to equal it, so I'll fill it in. And then x is greater than that. So that's everything to the right, all the way up to the infinity. So I've got 2 regions in my answer. I've got from negative 8 to negative 2, and then I've got from negative 2 to infinity. So that's just my number pieces. Now I need the symbols. So infinity always gets a parenthesis. The negative 2 is open. We're not equaling it. So it also gets parentheses. And we'll stick it together with a U. But the negative 8 is allowed to be equal to negative 8. So we give that the different symbol, the bracket.
Confusion was regarding about how like there's mostly the denominator, it can't like be undefined, but like what cases is it for the numerator? We have a square root in the denominator of something else in the numerator, how would we be able to tell the difference?
So in the numerator, generally like whatever's there is totally fine. Like it's okay for the top of a fraction to be 0. It's just the bottom of a fraction can't be 0.
So the only exception would be like a square root.
Yeah. So square roots, we can only have the inside greater than or equal to 0. So whether it's on the top or the bottom, the square root always has that greater than or equal to 0. If it's on the bottom, it also gets the added and don't allow it to equal 0. So we just end up like scrubbing the equal 0 part. If it's a logarithm, so if I have the log of some expression, then my domain restriction is that expression is strictly greater than 0. So if I mix a log into this equation, whether the log's on the top or the bottom, whatever is inside the logarithm, I write that greater than 0, and then that's another inequality that I have to merge with all the other results in my number line. But most of the ones we look at, the domain restrictions are typically just coming from whatever is on the bottom is set equal to 0, and that's your don't let it equal that value. All right, we probably got time for one more. And remember, I've recorded all of my review sessions and I posted the links with the question numbers I covered. So if you're like, how do I do number 8? You can go look at all the video names and then the one that has 8, and then it's listed in order. So if I covered it like as the fourth problem, like fast forward through like 30 minutes and then it should be there. Or maybe it'll only be 20 minutes. I don't know. It depends on how long the problems are.
Over a problem.
Yep. So problem 14 itself is a little bit more complicated than what's on the test. On the test, one of the points we give you is actually the starting value. So our algebra work here is going to be a little uglier. But they're telling us this is an exponential. So y equals a times b to the x. And then I have two really gross points. So I'm going to plug those xy points in for x and y in my function. So I'm going to have equals a times b on both of these, but now I'm going to fill in the numbers. So my x value is -3, so that's my power for b. And then it equals to crazy fraction number 1, -1536 divided by 343. And then my other one, x is -1, so I put -1 in place of x. Y is -24/7, so that is what it is equal to. Now I have two equations with two unknowns I can solve. It's just going to be a little ugly. All right, so our b to the -1 is a little less complicated than the other one. It really doesn't matter which one we solve, but I usually solve for a because the a doesn't have a power on it. So the b to the -1, I'm going to multiply by b to the +1. So b to the power times b to the power, I'd add the powers. B to the 0 would just be 1. This would leave me with a by itself. And I'm just going to have times b to the first power. So that's -24b/7. Now I'm going to bring this over to my other equation and write it in place of a. So -24b/7 times b to the -3rd equals horrible fraction. So that b to the first times b to the -3rd, I'm going to add those powers. So the b power is now the -2 power. And now I got some fraction nonsense to play around with. All right, so we're going to try to get b by itself. So the next thing we're going to do is we're going to get rid of the -24/7. So I can divide both sides by -24/7. And this is where you definitely want a calculator that is comfortable with fractions. So let's see. So the 1536 divided by 24 ends up being 64. So 343 and 7 like reduced to 49, and then the 1536 and the 60 and the 24 end up dividing and become 64. So we get positive 64/49 equals b to the negative second power. Now to get rid of the negative second power, I can't multiply by an extra b because then that would put a b on the left side. So I can only raise both sides to an appropriate power. So I want to figure out, what do I multiply to -2 so I end up with b to the first. So since it's -2, I need my power to be negative. And then for the 2 to turn into a 1, I need to divide by 2, which means multiplying by a half. So it's the -1/2 power that we're raising both sides to. So this ends up becoming 7/8. Now that I know what b is, now I can bring it back into my formula for a. So -24 times 7/8 divided by 7. And our a value actually ends up equaling -3. So final answer, sorry, they wrote it in terms of y. Y equals -3 times 7/8 to the x. So on the test, the points will be given, but one of them will be 0, a number. So that one will just straight up give you your a value. So you'll only have to do the b value. The b value itself, though, will be ugly. It won't be a pretty number at all. Then the question is going to ask a follow-up. So you're coming up with a formula that's modeling some environmental thing. And then it's saying, like, using your formula, predict what'll happen in this future time. So you just take the time number, shove it into the formula, crunch it up, spit the answer out. So this one is a free response. This is another one that's worth 10 points.
What's roughly on the exam?
The exam's still 100.
Still.
Yep. So there's 3 questions that are worth 10 points. All the rest are worth 5 points. So that's why it's 17 questions. It's like, oh, I forgot how many. It was in yesterday's video. It's like 8 or 9 multiple choice and then 9 or 8 free response. I forget if it was 8 or 9.
And our exam is in this room, right?
Our exam is in this room and it is on Thursday, so 2 days from now.
Sorry, I know everyone's asking these questions.
How much time do we have roughly?
We have an hour and 50 minutes.
50 minutes.
1 hour and 50 minutes. Yeah, so it's 110 minutes.
How much is the practice work for?
10 points on your final exam grade.
Done.